What do we have here?
Now we're going to talk about, we just finished doing the wedge cylinder heads.
This
now
looks
we have,
like a Honda here.
Yeah, this is a Honda 4V, and what I'm going to have to highlight is there are differences.
What is this?
This is a Ford 4.6.
4.6.
I'll show everybody later on. Now we talked about previously on the segment before this about swirl and
Tumble and swirl.
tumble and swirl. Now when you look at this Honda head or Acura,
Let's move this on.
all right,
Okay.
what it has is not really much swirl. It just have a tumble situation because a port angle comes in here right at the top of the valve, and all it does is do this.
That's tumble.
Now, yeah. Now certain engine designs, they tumble in reverse, and actually instead of propagating the flame or enhancing the flame, it tries to snuff it out. I'm not going to say who's that manufacturer that does that, but they do it for emission purposes. And when the people use that kind of cylinder head, they go backwards in power because it swirls. I mean, it tumbles contrary against the flame front.
Oh.
It kills the flame front.
Okay.
So what you have here is this. It comes in, tumbles this way, or maybe this way, more likely this way.
Like where it's standing, like probably a counterclock.
Yeah, it goes this
In
way.
a clockwise.
Clockwise. Looking at it from the right.
Mm-hmm.
Okay, so now it has that. Now
this is intake. This is
that's
exhaust. Okay.
Now again, what I said about the previous article about the crossover, where the standard wedge comes in here and comes in and goes the other way. That tries to limit reversion. Now, a port that flows good one way will also flow good in reverse.
In reverse.
Now,
that's efficiency.
Yeah, that's efficiency. The problem here is that what comes in quick and goes the other way also backtracks just as easy. Now, this is reversion prone. Comes in, it also wants to migrate back into the combustion chamber.
Back into the intake.
So that's basically like an inbuilt EGR. You don't want that for any kind of racer. So the situation, how do you enhance mixing in this kind of combustion chamber? Here we have the second example. If you notice, this one here has this area here.
You've got this.
Right, the quench pad, which is missing here.
There.
Now, the purpose for that is when the piston comes up, it pinches it and throws it towards the center.
Directs it towards
the center of the spark plug.
Where the spark plug is.
Now, if you utilize your quench clearance correctly, let's say 30, 45, as tight as 25 in some engines, but anything above 55 or 60, you lose this element of quench. Or what is another word for that?
Chamber.
Quench pad or a squish pad.
Space.
Yeah, squish pad. Now, when the squish pad is utilized, the piston comes up, flow here, it intersects, either it goes this way or that way. Okay, so that's another mixture motion that's inside the combustion chamber, which is missing here. It doesn't have that. So guys that are really good, they filled it in.
They'll put in.
They weld it.
They weld it in.
Right?
They'll put a quench area.
Put a quench in it. All right. Now, let me caution everybody that there are people with supercharged turbo cars, they don't believe in this quench. They say the boost in itself creates its own mixture motion. True,
yeah.
maybe.
Or it just pressurizes it more.
Right, it just creates its own mixing process. Maybe, maybe not. But I always like this quench.
You can gamble on that, or you can just be sure about it.
But most advanced cylinder heads have this. So if you don't believe in this thing, but the trend is everybody has a quench pad. Now, what do you do to create some kind of swirl? Some guys put a 45-degree here and a 52. They change the
angle,
the seat angle, so that you have some kind of a pulling situation to create this kind of mixture motion, like a clockwise or counterclockwise.
Very creative, huh?
Yeah, you have the swirl coming in, and then if you have two uneven flowing intake valves, guess what? You're gonna put a twist to it. If one valve is flowing better here or there, it'll twist this way. All right? Okay. So that's what you want to do. You want to put some kind of mixture motion in there, a mixing situation. Now, Ford did something else, which they did this. You have one square port and you have one oval port. Now,
Yeah, yeah. Here,
what-
here. Let's show them.
yeah,
Okay.
right. This too changes the characteristic of the flow coming in. What it does, it creates a swirl motion.
It makes a swirl.
Yeah. Which is pretty good. And the funny thing is that everybody discovered this, all right? That, oh, they just want the standard intake port like this. But actually, some of the fastest 4.6s use this kind of cylinder.
Right. Uh-huh.
So,
yeah, it's actually rectangular.
it's telling you something, all right? So this two uneven port creates a swirling situation,
Creates an swirl.
which is not possible with this,
Yeah.
all right? So the only way you can do that is you either install a bigger valve. Okay, granted, let's say you have a 45-degree seat. You go 1 millimeter over here or 1.5 millimeter over on one side. There's benefit. There's benefit to that because one valve is going to flow a little bit better than the other side. So it'll do this.
They'll give it a swirl.
Yeah, it comes in, tumble, come into the chamber, or get piston come up. Now you have one with an oversized valve, or you have a different seat. It come in a little bit uneven, so you have this.
It creates
This and this.
Mhm.
All right. So you want to,
That's a very good thing.
yeah, especially if you're normally aspirated, why not?
Why not?
But I tell you what, turbo probably works just as well. Everybody says, oh, just like the old belief, oh, when you have a turbo, you don't need that runner length. You can make the manifold short. Nope, still lose low end torque. Even though you're boosted, still lose torque. So runner length, swirl, they're all coming
That
to play.
runner is very important.
Yes.
That runner is very, very
Yeah.
important.
Now, some of the 4V heads out there with a shallow chamber like this, on the flow bench, when you increase that, well, you port to take advantage of the short side, you get an increase in flow at the flow bench. Looks good on paper. But I can't tell what manufacturer. One manufacturer dropped the floor, contrary to what is the popular belief, that you don't drop the floor.
Contrary to
Actually,
textbook.
yeah, it actually, they cut and dropped the floor a little bit
Mm-hmm.
because there's a shallow chamber. It lost on the floor bench, but it got faster at the racetrack.
Ah.
Now we have two illustrations here of what actually Ford did. I don't have the proper engineering drawings, but I remember this. It was in a discussion, in a technical presentation that they did. I'm gonna have to ask Orville Tucker, Matt Tucker's father, who worked at SVO at that time, see if he remembers this scenario as far as the 4V heads. What we're looking at here is the ideal exhaust port. It's not a high port, but it's got a very decent short side radius, almost mimicking the long side. And what you're having there is actually has a funnel effect. Okay, and once they travel upwards, they tend to stay in uniformity, or flow-wise, they're almost equal. Not all the way equal, because this is a little short, there's a long side, but you don't have a breakaway angle here. And if the changes are about 15 degrees departure from the long side, then you have a little turbulence. What actually happens starts to roll here. Now, from what I think they were trying to say, when they dropped the floor, that showed really bad on the flow bench, but when they tested at the dyno and eventually at the racetrack, it picked up power or picked up speed, an indication that it's making more power. When they mentioned, and I'll try to find that engineering article from SVO Ford, I think it's the Coyote exhaust ports that they're talking about. But what they said was they dropped the floor, which I feel this is what they did. I didn't see the cutout on the exhaust port. But what you have here is that when you pull away on the floor, what you're going to have, unlike that, is you're going to have the flow come in, and here it's gonna do this. Okay? And you're gonna have some kind of turbulence on the floor of the port. Low lift here, when the valve is partially open, you have something that the air can bank on and stick to on their way out to the downstream or the primary pipe from the exhaust port. Now, when you do this, it looks horrible. And when you flow test this, you will really see that this would flow a lot less, because this is what's happening here. You got turbulence. When it's turbulent, this is the exact port diameter that you're working with. Unlike here, it's more larger. All right? Because if you have a more laminar flow on the floor, as on the long side, that's what you're gonna see. Now, what you're looking at here, this I feel is what happened. I will try to talk to Orville Tucker and see what he says, if he remembers this. Because what happens here is that when it does have a turbulence, the velocity of the outgoing exhaust is significantly reduced. Therefore, when it's significantly reduced, the pulling effect from the intake valve, all right, so let's say the intake valve, when your overlap, instead of having it go in to the chamber here, if it's got a strong signal like it is here, wow, I'm really messing up my drawing. Okay, if the signal is very strong, the incoming flow will come in and a lot of it will go out, and you're blowing through the exhaust, and you're losing your dynamic compression. That the dynamic compression is the actual compression you catch inside the cylinder. If the exhaust is too good, this is what happens. You're blowing some of the intake column or overdraw. Intake, overdraw. Okay, it goes through the exhaust. But if you kind of impede, and like what I'm saying with one of my videos when I was talking about putting a smaller exhaust valve netted you more power, and we proved that many times. Like single angle on the exhaust, or a smaller diameter, or which this is not very good, when you pull away the floor or you drop the floor, that is bad news, according to the flow bench. But since the ability or the propensity of the intake column to come in, like in here, goes out the exhaust, it doesn't pull too much, and it goes under the valve and stays in the combustion chamber. That's why sometimes when you're having too much of a good exhaust velocity or flow in the low lift region, it will do an intake overdraw straight to the exhaust. Bad news. Now, some of you will say, oh, but now that won't flow as much at high lift or maximum flow rates, full throttle and everything. But the truth of the matter is, this throat diameter is the deciding factor. Okay? If that diameter is smaller here, that will definitely flow more. But let's say all else being equal, but you have this issue here at hand about the floor pulling away. That is bad on the flow bench, but actually better on the 4V small block Ford Coyote engines and the older generation 4.6. This is what you're looking at. I'm not worried about this. I'm worried about the throat diameter. Everything else being equal. This is the deciding factor. Of course, to a certain extent, how much is the departure angle or the exit angle of the exhaust. If it's a high port, of course, it's going to flow better. But all else again being equal, like this both of them have the same departure angle coming out of the cylinder head to the header, something that pulls away like that. Okay. You can elevate some of this situation if you made your lobe separation a little wider, so your overlap would be less, and you don't have too much of a intake overdraw to the exhaust. Whereas here, our old tendency before was to put a lot of overlap to try to fix that bad exhaust port. Yes and no. When it's too good sometimes, you're better off kind of restricting the flow, as we found out with this new generation 4-valve heads that Ford has. Like I said, let me repeat, if I can find that article again, and I'll try to repost it, and because this is back in 2010 or 2012 when I first came across it, and it caught my attention, and it led to me to believing that at that time we have too much exhaust port. It's true then, and it's true now. Okay, so we went from doing the improvements on the exhaust port was overkill, and then we added more duration on the exhaust. You know, we run what, 285 intake, and then 298, 300 at 50 on the exhaust to compensate for the so-called bad exhaust. And then we kind of pulled back. Everybody ended up with 284, let's say, or 280, and then, you know, 900 lift. And guess what happens here? 800, 80,000, 100,000 less lift on the exhaust, whereas the duration still, you know, 8 degrees, 10 degrees over the intake, but we lowered the lift. That was already an indication of what was going on. Here, that is something to think about. All right? So, like I said, sometimes the flow bench can fool you and lead you the wrong way, and sometimes you just gotta test. That's why you come across when people said, well, we ran the head that didn't flow as good as the better #1 cylinder head, the main racing head, but the doggone worse flowing head, exhaust or intake, whichever combination, produce better track times. Here's one scenario. Okay? Intake, overdraw to the exhaust. Same thing with the 4V heads. And I'm sure a lot of the imports and everything else the same way. When I dealt with Mercedes-Benz, their exhaust valves are real tiny compared to the intake. And I was very impressed with that head, which is in the intro to this video. Okay? So, think about it, guys. I can tell you who what manufacturer that is. So, for some of you 4V guys, don't eliminate it completely. Just drop it slightly and test at the track. You don't just go there and say, oh, it's perfect. Trial and error.
Word to the wise.
Okay?
One adjustment at a time. Okay?
Yes, one change at a time.
Don't
Okay.
try to change 3 different things, because whether you gain or you lose, you don't know where you got it or where you lost it.
Exactly. Yeah.
One
Where
change
was it
at a
there?
time.
One change at a time. So again, drop the floor a certain amount, not all the way, because if you take it off completely, you just ruin it. But it breaks the norm that when you drop the floor, which is a no-no really, then you test, you might see some power thing, even though the flow bench said no. Right?
And you really won't know when you've gone too far until you've gone too far.
Yeah. No.
So
Right.
it's a work in
Yeah.
progress, and it's an expense in progress.
Right. So just again, it may work on the Honda, but I see it here is a little bit deeper. If you look at, this is a smaller chamber, but it's deep. There's a bigger chamber, but it's shallow. All right. I tend to like this better. I don't like big combustion chamber. Big combustion chamber, they take heat. Yeah, there's low compression, lower compression. You have to put a dome to get compression out of it. The bigger chamber takes in more heat. Okay, you want heat to stay there and make more power. This one absorbs more heat, a bigger chamber. This one does not. So I think that's. Oh, and then again,
smaller hemisphere. You're right.
Since this old video from 2012 touched on the subject of combustion chamber volume and why we need to have, well, for me, on opinion, a smaller combustion chamber depletes itself of exhaust gases a lot readily or a lot faster than you would with a bigger combustion chamber. The more volume there is there, there's less chances of evacuating it quickly. All right, so when you have a compact chamber, it's easier to deplete, and also at the same time, the smaller chamber, since the space is more confined during the overlap, instead of trying to draw through the big combustion chamber, a compact combustion chamber, as soon as it draws an exhaust going downstream and the intake valve starts to open up, the exhaust valve starts to close. The smaller combustion space reflects this low pressure area coming out of the exhaust, okay, and pulls the intake right with it, okay. Plus, with atmospheric pressure, or if you have boost, whichever one, the smaller combustion chamber will reflect this low pressure area from the exhaust port low pressure area to the intake port low pressure area. It gets in a good yank, and you're not going to get the same signal or just as strong a signal when the combustion chamber is large or very big. It's kind of the signal is deadened quite a bit, as opposed to a smaller combustion chamber. It's quick reacting to exhausting, quick reacting into drawing during the overlap. All in all, it's, well, should we say, it's an advantage. Now, the only issue I have sometimes, somebody called me before and said, hey, we got a Honda and we have a dome on our piston, and I'm really concerned about the spark flame front impeded by the dome. I said, well, you shouldn't worry yourself about that. You're thinking V8 or some of the inline 4 and 6 cylinder engines where the spark plug is towards the bottom of the cylinder head or the combustion chamber, where it has to climb over the dome for the flame front to get to the other side. On a 4V or even 3V with a centrally located spark plug on the roof of the combustion chamber, the chamber's flame front emanates from the top of the combustion chamber, and the dome is below it, so there's no issue about impeding the flame front from propagating towards the whole diameter of the combustion space or the piston. So there's no need to worry about that. And again, some of these cylinder heads have dual spark plugs. Oh, excuse me. Boy, it's already late at night. I'm still getting phone calls. Anyway, excuse me. Now, on that regard, dual spark plug, there's less chance of secondaries or detonation from happening, especially on the outer edges of the intake valve towards the cylinder wall. That isolated area, even with a quench pad or a lack thereof, the dual spark plug expansion point or the flame propagation point or flame front, basically it consumes that area before there's an additional pressure and temperature buildup that creates secondary ignition sources. It's very important, and it's a good design. Okay, so now let me touch base real quick. Wow, I'm gonna shut this phone off. I also have one thing about quick reaction to about dome. A dome on an NA engine is bad, okay, because if the spark plug location is not very good, it can impede the flame front from developing across the cylinder diameter. The only good part with a dome is on nitrous engines, because nitrous, the more nitrous you put in, the faster the flame front starts to accelerate. And the only way that something like this is controlled is by softening the heads, where you put a little taper on the quench side to try to get that to cover some of the isolated areas of the quench pad, or I run a V groove on the combustion quench pad. I will show that here soon. But the dome, okay, if you're running inline heads especially, or even some of those canted valve heads, the dome actually becomes a speed bump for the flame front from accelerating from a fast burn to an explosion. Sometimes the dome kind of like slows that flame front. Basically, it's a speed bump. Okay, and it keeps you out of trouble. I know these people, they're overseas, excuse me. Yep. Anyway, that is exactly what's going on there. The flame front wants to speed up to an explosion, and the dome, becomes a flame limiter in a sense, or a speed bump for the flame to slow it down a bit, just like the quench side is. Now I hear birds, or owls, whatever they are. Boy. Oh, also, if you notice this V8 cylinder head from Ford, look at the diameter of the intake valve as opposed to the exhaust. Big difference on the Japanese engine here. From a distance, it's kind of hard to tell the intake from the exhaust. You can, sometimes I deal with these things in Asia, and the exhaust valve is so close to the intake, and I keep telling people that it's a power loss. Okay, and I guess bad habits are hard to break. If they think you put a bigger intake valve, you got higher compression, you also have to put a bigger exhaust valve. Nothing could be worse. Okay, and you gotta, with my research with Gage Motorsports, Max Gregorich, we did gain power with a smaller exhaust valve, no doubt. But on single piston, he said there's an exception. At the very high RPM engines, you still need a somewhat decent amount of exhaust valve to help yank in the intake column into the combustion chamber. At the same time, trying to limit the intake overdraw from going through the intake column to going straight to the exhaust port. And they try to limit that, and there are ways of doing that. And at the same time, on a single piston engine, you don't have the convenience of adjoining cylinders or cylinders next to that one that's firing and exhausting from helping scavenge and pull the other cylinders with it. On a single piston combination, you're dependent on that one exhaust port and that one intake port and that one piston to help induct the air in column and exhaust that. And so a singular action, not like multi-cylinders or in fact even twin cylinders, has some kind of help. You don't have that with a single piston. So there's an exception. You can't go too small on a single piston. It needs a certain amount of diameter to help pull the intake column in the combustion chamber. Just a side point. Right, now again, another point. A lot of people, I see it out there in Asia, in the Philippines, Singapore, Thailand, I see a lot of 4V heads where the intake and exhaust is almost close to each other.
Almost the same size.
Guys, that's a no-no, okay? That's a no-no. If you look at this thing here again, it's a drastically smaller intake to exhaust than this. Now, I see a lot of those in Asia, the exhaust valve is just as big.
Just as big as the intake.
Wow.
I know.
Not only is that dangerous because you have this situation here. Spark plug, close, you get cracks.
Fractures.
Okay, at a very high horsepower level. This part here collapses. Alright, and then the seat falls off. Here, you want it to be as far as possible. Alright, so again, contrary again to other opinion, I don't like to increase the exhaust size. I keep it where it's at. Maybe 1 millimeter over if you're not really satisfied, 0.5 millimeter. but I will not go any more than that. And then I try to put as big an intake valve as much as possible on the intake side.
Mhm.
Same thing here.
Without,
Look at that.
without trying to, yeah,
Sure.
exactly.
Look how much closer that is. Look how far that is.
Actually, look how close it is to
Yeah.
the rim.
Sure, sure. Okay, so again, the
Actually,
cracks are here. This situation, you don't get enough cooling between two exhaust valves. This becomes a failure point. All right, soft spot on the cylinder head. So again, a lot of people will probably tell you, put a big exhaust valve. Well, case in point, nitrous heads from, again, a bunch of pro stock guys are Glidden and Edelbrock. If you look at their nitrous head, the exhaust valve is actually smaller.
it is. I wonder why they do
Yeah,
that.
okay. The higher the horsepower, the smaller the exhaust valve. The higher the compression, the smaller the exhaust valve. But the bigger the intake valve, okay? That's a given. But you guys, especially the ones in Asia, try to think about that. You don't want to do that. Okay? I'll write an article in Para pretty soon about this situation about a smaller exhaust valve. That's
The bigger is
Yeah.
better syndrome.
Yeah. Okay? So I think we're good.
Okay,
Right?
so
So, yeah.
that's our topic for the
All right
week,
then.
guys.
Thank you. Take it easy.